Fall semester of this seminar. So we're very happy to start this semester with a talk by Zexin Pan. Sorry for the pronunciation.
Oh,
So,
that's fine. That's fine.
he did his PhD in Stanford under the supervision of Art Owen and finished basically 1 year ago now, I think, on the topic of superpolynomial accuracy of randomized nets using the median of means. Okay. And now he's a postdoc at RICAM, the Austrian Academy of Sciences in Linz, I suppose.
Yes.
And he's agreed to give us a talk today about, as you can see, media and quasi-Monte Carlo for high-dimensional integration. So thank you for agreeing to give a talk, and please go on.
Okay, cool. Thank you for the introduction. Yeah, my name is, well, I mean, like, so the true pronunciation is like Zexin Pan, but I usually just pronounce it like Zexin Pan because I think it's easier for the English speaker to pronounce it. So anyhow, so today I'm going to share some kind of recent progress in the high dimensional integration called median QMC. And you can see the catchphrase here is nearly optimal without prior knowledge. So let's start. So first, let me give a outline of this talk. So in the first part, I'm going to give an overview of just basics of like quasi-Monte Carlo methods. I definitely don't assume any of you ever heard of this method, so I will start very basic concepts and give some examples. And then in the second part, I'm going to talk about a probably the easiest method in QMC called lattice rules, and I use it to illustrate the idea of like median QMC. In part three, I'm going to apply this idea to the L₂-approximation problem and get some maybe surprising results. And the fourth part is sort of the bonus part. So I usually only give like 20 or 30 minutes talk. So I'm notified that I get to get 15 minutes. So I think like last time I give 15 minutes talks like on my defense. So I'm not very confident like what to put there. So I just decided to put another part which is more related to what I'm like researching on. So but that being said, so it's an extra part. So I don't want to be too stressful for you guys. So in the first part, I'm not going to do any hard proofs. So you can basically just sit down, relax, and I'm going to show you some like tell some stories, show some pictures. So yeah, so that's kind of the overall. So basically, you only need to stay concentrated for the first three parts, which I assume is like a little bit more than 30 minutes, I hope. So let's start with the first part, which is an overview of the QMC methods. So first of all, what is QMC? So as you can probably already tell from the name, it has Monte Carlo. So it's very similar to Monte Carlo. In particular, the problem setting is basically the same. So here we have a function defined on the unit box. We have an integral of this function, and we don't know this integral, so we want to estimate it. We estimate by an average of n function evaluations, and of course we have the right to choose where we evaluate those functions. And at this point, you may already wonder, like, okay, why is the unit box? Well, it's actually the unit box is actually modeling the d pursued random numbers. So in particular, in this context, we view random variables, or more generally randomized algorithms, as actually a deterministic functions from those pursued random numbers to the output. So for instance, in your program, you may want to call some random number generator. So when you do that, what it does on the programming level is that the program actually call a pursued random number, which returns a number between say 0 and 1. And then the program do some transformation to get to the actual random number you want. So on the algorithm level, we really think of like any kind of randomized algorithms, actually the deterministic algorithms, once you fix those pursued random number inputs. And that's why like you sometimes see so in those simulations, you can set the random seeds. Once you set the random seeds, the pursued random number generator give you exactly the same pursued random numbers. So that's why your output is exactly the same, because on an algorithm level, it's really just a deterministic algorithm by taking into account that pursued random number inputs. So, okay, so you may wonder, okay, how QMC differs from just plain Monte Carlo. On the right here, I have the very classical Monte Carlo points. So Monte Carlo points, so I mean, this comes more precise, like the pursued random numbers generated by those pseudo random number generator are supposed to mimic the behavior of independent random variables distributed uniformly on the unit box. And you can immediately see the issue here. So because they are supposed to be independent, so you can see like on many places we have like those kind of empty holes. And if you think about like integrating a function, those empty holes, basically you don't know anything about the functions inside empty spaces, and that can cause you error. And because it's Monte Carlo, so you cannot really control the points to go into those empty holes and actually get you more information. And also you have those clusters, which is basically a waste of sampling. So that's like the issue when you use like Monte Carlo points. So in contrast, we have on the left the QMC points. So QMC points are not trying to mimic the behavior of independent sampling, but rather it's trying to distribute the sampling in a way so that it explores the unit box as quickly as possible. So you can see like here the point size is very structured, and here, like, yeah, you kind of like eliminate those empty holes in a more efficient way. So I will give more details later. So here's another way to look at QMC. So you can kind of think it as like on the spectrum. So on the one end, you actually have the classical quadrature rules for the numerical integration. Examples are, say, midpoint rule or triple rules. So those integration methods use structural point sets to get like fast error convergence. But the issue is that it suffers from the curse of dimensionality, especially if you just use the naive, tensor product construction to extend it to higher dimension. Monte Carlo, on the other hand, use those kind of independent points, and it gets a dimension independent convergence rate, which is the standard deviation over the square root n. So you have dimension independence, that's good. But the issue is that, well, the square root is just too slow. If you think about like what you have in classical quadrature rules, you can often have like n to the minus 3 or 4 with those kind of higher order like Gaussian quadrature rule methods. So QMC is in this sense, like trying to interpolate between the two. It tries to use also structural point sets to get convergence rates faster than Monte Carlo. At the same time, it also does a better dimensionality dependence compared to the quadrature rules. So it's kind of like trying to do the sweet spots of the two methods, if you want to put it that way. So before I talk about like specific QMC methods, let me just give you some examples to let you know like what kind of the problems QMC practitioners have in head when they kind of design those algorithms. So one area where QMC is particularly successful is finance, particularly called option pricing. So here we have BT, which is a standard Brownian motion here. And we'll say we want to know the expectation of a function of Brownian motion. And so here is an example, which is Asian call option. So the function is given below like this. So first of all, what is an option? So an option, to put it in a simple way, an option allows you to, in this context, say trade stocks at a non-market price. So in this example, ST here is the stock price modeled as a geometric Brownian motion, and then the integral from 0 to t divided by t of ST computes the average stock price over this time period. And then these options compare this price with what is called like strike price K. So what it does is that if the average price is beyond K, what you can do with this option is you can buy those stocks like sort of the average stock with price K despite the actual market price. So by doing so, you can make a profit because you buy something more expensive with a cheaper price. On the other hand, if the average price drop below K, then of course, you don't want to buy the stock with the price K because it's more expensive. So do nothing. So that's why this function is the max of this difference with zero. Because once the price drop below K, you do nothing. So you don't lose. So you don't make progress, but you don't lose. So that's what this function does. It basically gives you the kind of profit you can have by having this call option. And then, okay, so because it's it can potentially make you some money. So of course you can sell this option, and how much you should sell it. Well, people agree that it should be the expected profit you get from this option. So that's why like the option pricing problem is about computing the expectation of this thing. And in this context, the expectation of this function, and here's the ST is a geometric Brownian motion, so it has a Brownian motion hidden there. Okay, and then here comes the question of, okay, how you actually simulate a Brownian motion on a computer. So of course you cannot simulate the actual Brownian motion because it's a continuous trajectory. So what you do is you discretize it over several time spots. And if you do a naive way, which you can often do, say when you use Monte Carlo, is to just like do sort of like a Euler ODE kind of progression here. So basically, what you can do is you simulate the next time spot based on the previous time spot plus a Gaussian fluctuation here. The ZJ I already is like a standard Gaussian random variable because I single out the kind of scaling factor in front. And you can do this like recursively to get also time points, also value of the Brownian motion on the time spots. So here is I write it as a function of the standard Gaussian, and how you get from the pursued random numbers to the standard Gaussian. Well, there are several ways. One way, quite straightforward, I use here is to do the quantile function transformation, where you just put the pursued random number into the inverse CDF function of standard normal, and the output turns out to be standard Gaussian. So that's like how you write a standard Gaussian as a function of a standard of a pursued random number. So in this way, you have your function, which is originally a function of Brownian motion, approximately as a function of those standard Gaussians, which in turn are those pursued random numbers. And here the dimension D is like kind of like the your level of like how close you are discretizing this Brownian motion trajectory. And obviously, the larger the D, the better the approximation. So in the context of QMC, that's actually not the discretization you want to do. I mean, not the kind of like simulation you want to do. So here's a better way, probably generating a better result. It's called a Brownian bridge construction. So what it does is that it generates the Brownian motion locations at in this order. So first you generate the value at 1. Which is standard Gaussian, and then condition on the value of 0 and 1, you generate the value at 1/2. So that's this point. It's again a standard Gaussian if you do the conditioning. And then with the value at 0, 1/2, and 1, you generate the value, I think, at 1/4, which is, I believe, this number, and then 3/4, which is probably this number. So again, that's standard Gaussians under the conditioning, and then you can just progress. You generate also values at 1/8. I think yes, this one is 1/8, 1/8, 1/8, 1/8. So you have like full 1/8 points. And you generate those points condition on the values you already generated before. And at any point, you can just connect those points to get an approximation of the Brownian motion. And also, if you really want to construct the entire Brownian motion, you can always do so by filling the empty spots with the Brownian bridge. So that's why this construction is called Brownian bridge construction. So why is this construction maybe preferable compared to the previous one where you kind of do a Euler progression? Well, it's because like in this construction, what you do is you first kind of get a sketch of this Brownian motion. So you can imagine that on say a regular problem, say the stock price. So the sketch maybe already give you most of the information of how the stock price should go, and those finer details only give you a small perturbation. So in this sense, like also small details you add later is not as important as say the first 8 values you put there, which gives you this sketch. So in this sense, the problem dimension might not be too large too much larger than 8. So that's like how you kind of like in this sense reduce the dimensionality by organize the simulation in a better way. So here's yet another construction of Brownian motion. Because we know a Brownian motion is a value, it's a function between over 0 to 1. So you can do a Fourier expansion in particular. So here is like a Fourier expansion. You first remove the kind of the trend term, and then with the remaining term, you can do a sine function expansion. And so in simulation, of course, you cannot do an infinite series. So what you do is you can do a truncation. And then below is something you can actually simulate. So if you simulate the variable z0 to z0, then you can actually, so you actually simulate a function over 0 to 1, and you can replace it replace the Brownian motion with this approximation and do your simulation. And in this example, you can see quite clearly that how the so sort of like the later dimension decays, because you have a scaling factor here. You have the sine function divided by j. So in this sense that zj, also the zj here is a standard Gaussian, with larger j, it actually contributes less and less to the actual output of the Brownian motion because of this scaling factor of j. So here's another example, which I think I guess this one is more familiar to the UQ community. It's the random PDE problem. So here I have I think elliptic PDE here, and then we have the coefficient the 8a here. So this omega is modeled as a random source. X is the physical coordinates. So basically for every simulation, you can solve this problem, solve this solution u as a function of x, and then also as a function of the random input omega here. And we often assume like the random field has a series expansion, something like this. With expansion in the say the eigenfunctions here. And in modeling, we can model the random coefficients aj omega here as actually a function of the pursued random numbers with some kind of decay in j. So in this sense, then well, so if you simulate a smooth random field, that this decay is often guaranteed, and then if you do Monte Carlo, what you do is that, of course, you do a truncation, and then you simulate those numbers with the pursued random numbers. And if you just replace those pursued random numbers with the QMC points I'm going to introduce, then you have the QMC version of this problem. Yeah, so in a sense, it's very similar to the Brownian motion I have shown before. So after truncation, even though you truncate infinitely many eigenfunctions expansion here, the actual loss is not like infinite. So it has a well-defined set that this problem is sort of finite dimensional. Okay, so let's go into the part 2 where we actually began to talk about the actual QMC methods. And I have to confess here that because I mainly do theoretical methods, so that's like so all the examples you have seen like I gave there is probably the only examples you ever see in this problem. Now we are going into the area we do only like abstract problems. So okay, let's record that we want to do a numerical integration problem here, and we approximate the integral value by the function average here. And the method I'm going to introduce, the lattice rules are particularly suitable for function periodic on the boundary. So in particular, what we will assume about this function is that this function is continuous. It's one periodic in each direction, and also this function has a Fourier expansion like this, and we assume this Fourier expansion converge absolutely over the unit box. So it's very nice with respect to the Fourier transform. And then we can define the sorry, I can't pronounce his name. Colobos norm here, so which is the weighted sum of the Fourier coefficients, as you can see here. So the weights are given below. You don't have to memorize this because I'm not going to actually do any calculation with it. But let me tell you what those parameters means. So here you have alpha, which is the smoothness parameter. You can see like it's hj to the alpha, so it's penalizing high frequency Fourier coefficients. And when alpha is the integer, it's literally the number of derivatives this function f has. So it's the smoothness parameter. And then you have the coordinate with gamma 1 to gamma d here. So what this thing does is that a small gamma j, for instance, is penalizing Fourier coefficients associated with coordinate j, which in turn is penalizing fluctuations. in the direction J. So why we have this kind of weights is to trying to model the fact that in those examples we have before, we have this phenomenon of the later variables actually have a decaying influence on our output. So it's trying to capture this fact by putting a decaying weights here. So for those kind of functions, there's a very natural method to integrate them, which is called the lattice, rank 1 lattice here. So what you do is that you grab a prime number n, which is the number of evaluations you want to do, and then also d numbers between 1 to -1. And what you can do is to set your numbers xk to be, so the first coordinate is z1 times k, which gives you, of course, the integer. You divide it by n, and then you do a mode 1. And then also where you do zd times k divided by n mode 1. And so first of all, why mode 1? Because we assume our function is periodic, so which means that if you sample outside the box, you can equivalently sample the function inside the box at the mode 1 position. So this mode 1 is quite natural if you think about your function is periodic. And here is a picture of, I think this is 89 points, Z1 is 1, Z2 is 55, and you can see these points that is quite uniformly distributed within the unit box, looking really nice. And well, set one is actually I tune it so that it's a pretty good one. You can also have like a really bad one if you don't tune it good enough. So here you can have Z1 equal to 1, Z2 equal to 1. That's the picture on the right hand side. So what it does is that every step it do a small progression on the diagonal, and also where you after you go to the end of the diagonal, you go back to the origin. So this one is also a letters, and it's obviously bad. Like you definitely agree that it's not exploring the unit box as well as the picture on the left hand side. So here is kind of the crucial question. Okay, how you actually like choose those kind of like generating vectors? So first, how we measure? So what kind of measurement we should use for those generating vectors? So because we are dealing with integration problems, so let me just define something quite intuitive, which we will measure it by the worst case error, which we said, okay, we have the letters defined by the input n as the generating vector z here. And then we can think about, okay, we have our estimate mu z, which is against the average of the function evaluations for where you evaluate the functions over the letters. And then you can minus it with the actual true value, so mu here. And then you think about like what's the kind of worst possible case when your function is over this kind of unit ball in this curve space. So this kind of worst case error is sort of like what you concern yourself with in the context of numerical integration. And well, this one, so here I'm going to do a little bit of calculation, but I think most of them should be quite easy. So first of all, you can actually compute this worst case error. So first you can compute this error here. This error is given by this sum of Fourier coefficients, whereas this h is over the due net minus 0. So okay, so what is this due net? So here I have the notation PZ perpendicular. So this is a set of the integer points for which this sum is 0 mod n. So in other words, it's a perfect multiple of n. So intuitively, this set is the set of frequencies that's confounded with the zero frequency due to the fact that you only do a finite sampling over the lattice points. And you can see in the proof like why this thing comes into the error. So here we have the first line, the definition of the letters, and then your estimator, which is mu hat z, is the average value of these function evaluations. Well, because we assume our function has a Fourier expansion, so you can just replace f by its Fourier expansion here. And then once you do so, you can you have the values xk here, and then you can put in the definition xk into here, and then switch the order of summation. So what you have is a summation over h now, and then inside here we have summation of k. And you can now look at this the summit here. So the crucial part here is that if this sums the sum over J1 to D, if this sum is a perfect multiple of n, then what we have here is 2 pi I k times a multiple times an integer. So this thing is always 1. So that's why this sum is going to be 1. And on the other hand, if this sum is not a multiple of n, then what do you so what's this summation is doing is kind of going through the unit root of one in the complex plane. So that's why this sum is going to be 0. So after doing the algebra, you on the right hand side, you come out to be f hat with h going through the do nets here. So do letters here. And here we do minus 0 because 0 is so the zero frequency is mu. So if you just move the zero frequency to the left hand side, then that just gives you mu our mu hat minus mu to be this sum of the do net minus the zero frequency. Okay, so I hope it's like a easy calculation. To you. And then with that expression, you can quickly derive what's the worst case error here. So the worst case error, which is defined by the soup over the functions over the unit ball of this error term, which I write out here. And then you can just do a Cauchy-Schwarz inequality to connect it to the corpus space norm we have there. And then you can notice here we have the first sum here, which is trying to mimic the form of the corpus space. Okay, yeah, I just cannot pronounce that word, which is kind of mimicking that norm here. And here we have the sum of the do nets and minus 0, while the norm actually sum over all the integer points. So that's why it's an upper bound here, which further is bounded by 1. So that's why you know that the worst case error is bounded by the second sum here. So that's the upper bound. To prove equality, you just set everything so that everything here is like an equality instead of inequality. So that's how you prove that the worst case error is this sum here. Okay, and now we have a form of the worst case error, and then we can, from this form, we can basically do some kind of like a minimization. So that's what actually do if you like ask me how to do this thing 3 years ago. What we can do is to do kind of like a minimization of this worst case error. And in particular, there's an algorithm called component by component construction, which is basically a greedy algorithms where you select your next component condition on the previous ones, and you kind of minimize functions that related to the worst case error in a greedy way. And this algorithm, well, I mean, if you want to see the details, you can check this book, which is, I think, the kind of the standard textbook for lattice methods. I'm just copying some results here. So the generating vector Z you generate from these algorithms has these properties, which is quite nice. So worst case error is almost converging like n to the minus alpha. And also, if you consider a setting where you have the dimensionality diverging to infinity, so that corresponds to the case where you say, if you think back in the random field case, you add more and more details to your random fields. And then in that case, if your weights, which is kind of the modeling the actual fluctuation, actual contribution of those each coordinate to the final output, if this weights decay fast enough so that some I show here is finite, then there's a sense of like this problem should be finite dimensional, and indeed you can bound this constant C eta here independent of D. So that's like how the QMC community like to say, okay, you kind of conquer the curse of dimensionality, because even if your D goes to infinity, your convergence rate is not impaired by the dimensionality here. So that's all very good. The issue, however, with this algorithm is that first, to start with this algorithm, it's a construction. So to start with this construction, you need to input a value of alpha and gamma. So for real problems, you may not know what values you put there. Say I have shown example, say Asian call option with some kind of like function you want to evaluate. So it's hard to figure out the alpha. Maybe you can figure it out by the smoothness of the function f, and it's even harder to figure out what the gamma should put there, because the gamma is supposed to model the decay of each variable to your actual output. Without further study, you don't know like how much each variable is actually contributing to the final output. And another issue is that to run this algorithm, you need some runtime. So runtime is like naively speaking D times n log n. So the D dependence here can be relaxed especially under a condition like this. But the n log n, you probably cannot escape it. So it's kind of annoying that you are doing n function evaluations, but you to just compute where you evaluate those functions, you actually spend n log n time. So it's kind of like annoying. And I think just beyond all of this, like when you try to program this thing, like this CPC construction is not something like trivial. So I remember like for the first time I want to run this algorithm, I just like stop at this step because like I just find the CPC step a little bit too annoying. So here comes our kind of our main character of this talk, and yeah, I'm just checking my time. So yeah, so now comes our main character of this talk, which is the median approach. So the median approach kind of remove all the kind of the troubleness in generating this the generating vector z by just uniformly choosing it from the set of possible candidates here. And you might think, okay, why this thing might work? Well, the key observation here is that if you just choose it uniformly, then with a successful probability at least 7/8, you can actually get also like good result we have just shown there, almost n to the minus alpha convergence rate, and also this dimensionality independence here. And let me just do a proof. So this is probably the hardest proof in this talk. So you can like after this level, everything else should be easy. So that's like the hardest part. So it's kind of anyhow. So let's start with this proof. So here I copy down the definition of the dual letters here for reference. So okay, so recall that we have our worst case error. So here for the easiness of computation, I just square it, which is then this sum here, h over the dual letters minus 0 of this inverse weights. So first what we do is that we separate into two terms here. So the first term is h over the where the every component of h is a multiple of n. So why we separate out this term? Because if you just look at the definition here, if h, all the components of h are multiple of n, then whatever generating vector you put there, this sum must be a multiple of n. So that means that this component is always in the dual letters. So it's kind of like the irregular part of this dual letter. So let me just single it out. So the good thing is that once you single it out, single out this part alone is actually only like n to the minus 2 alpha. So you remember we want to bound it by n to the minus alpha for the square root part. So n to the minus 2 alpha is okay for us. So we can just bound it and then just throw it away. So we want to bound then the second term here, which is the dual letters minus the irregular parts, the NZD part. And we can bounce the second part if we can show with for most choice of the generating vector z, the second sum actually contains no small inverse weights here. So how you do this? So the most important observation here is that if you have a vector, if you have a frequency h for which the components are not like a perfect multiple of n, then the probability that this frequency is in the dual letters is actually bounded by 1 over n minus 1. Because if you just look at the condition here, you need this sum to be 0 mod n, and you say, so it must has a one component that's not a multiple of n. So let's say hj is not a multiple of n. And you can recall that the n is actually a prime number. So if you learn some algebra, you know that mod n is actually a field. So what you can do is that you can inverse, you can take the multiplicative inverse of hj, and then you can write zj as a function of everything else. So that means that for whatever everything else you provide, there's only possibly one solution for zj here. So then because zj is uniform over the chosen from 1 to n minus 1, so, and you only have at most one solution, that's why it's bounded by 1 over n minus 1. So once you have this bound, what you can do is that, okay, because we don't want the small weights to be inside sum, so what you can do is that you can select a set k here, which is the set of frequencies with the smallest weights here. And then we control the size to be n minus 1 over 16. Then once we do that, then, well, by a union bound, with the bound we have above. So this intersection of this K with the dual letters to be non-empty, it can be bounded by a union bound of K over n minus 1, which is in turn bounded by 1 over 16. So that's how you can kind of with high probability remove the small weights you don't want in this sum. So with probability at least 15 over 16, we have the intersection to be empty. And now we can do a conditional expectation. So under the conditioning says the intersection is empty, well, we can bound this sum by what's on the right-hand side. Why is that? Well, if you have h that's in K, well, because of this conditioning, it's not in the dual letters, so it doesn't appear on the right-hand side. If h is not in K, then well, we just use the previous bounds, then the probability is inside the dual letters. It at most n minus 1 over n minus 1. So that's how you get this bound on the right-hand side. And okay, so you have a bound on the expectation, and the standard way to get to the high probability bound is to use the Markov inequality. So in particular, you can inflate the right-hand side by 16 times here. And once you do that, you lose 1 over 16 probability, and you can claim that this sum is bounded below by this 16 times of the right-hand side. And if you just count the 1 over 16 probability you threw away for the non-intersection condition here. So altogether, you have 8 over 7 of 8 probability for the non-intersection to occur, and also for this sum to be bounded below by 16 times of the right-hand side. And then we kind of like come to the end of this proof. So the only thing you need to do is bound this sum here, where we have this inverse weights, and you remove the smallest weights from this sum, and then you can do some algebra and bound it by n to the minus 2 alpha plus 1. And then you have a factor of 1 over n here. So that's how altogether you prove n to the minus 2 alpha. Okay, and you may say, okay, now we have a bound that's with successful probability 7 over 8. That's not too impressive. But what you can do is called median trick here. What you can do is that you can draw multiple of those kind of independent draws. So here I have R independent draws from the candidates here. And then once you have R independent of them, you can take the median of the worst case error. And then the median is below the same bound with a probability or with a failure probability exponentially small in R. Well, why is that? Well, just intuitively speaking, because the failure probability for a single draw is like 1/8. So if you have R draws, you expect on average you have R over 8 of them to be beyond this threshold here. But for the median to beyond this threshold, we actually need half of those simulations to beyond this threshold. So that's how like you can actually bound it by an exponentially small factor in R by some kind of say concentration inequality, for instance. And then, well, how you turn this thing into a bound you want? Well, here you have the median of the worst case error. You can use Zexin's inequality to move the median inside the soup and the absolute value here. So now what you have here on the left-hand side is actually a worst case error of this median estimator. So this is something you can actually generate for your algorithm. And that's how actually you get a estimator which with this worst case error n to the minus alpha. So let me just state it as a theorem. So for Z1 to ZR, uniformly draw from this candidate set, you can bound this worst case error of this median estimator by something converging almost like n to the minus alpha here, with a failure probability that's exponentially small in terms of R. And also you have the usual dimensionality condition. Okay, let me just summarize it by a table here. So here you have on the left-hand side the usual CBC construction, and on the right-hand side you have the median approach. So the CBC construction gives you the worst-case error, which is almost n to the minus alpha. Median approach gives you n to the minus alpha with a failure probability exponentially small in R. And the CBC construction requires you to import alpha and gamma. The median approach, well, you just generate them uniformly at random. You definitely don't need alpha and gamma there. the function evaluations, the median approach is a little bit more R times N. And the time to construct the generating vector, CPC construction, as I mentioned, it requires its runtime. For the median approach, it's basically trivial. You just put random numbers there. And then let's come to the third part, and I guess I'm running over time. So, well, I mean, I still have 10 minutes, but I guess I will just end with the part three here. So I think at this point, you can sort of say that, yes, the median approach gives you some kind of like lazy man solution to how to generate the generating vectors there. But it doesn't improve the convergence rate, so it doesn't kind of convince you to actually use that method. Well, here's a surprising example where you actually get a better convergence rate as well. So that's the setting of like a L2 approximation. So again, we assume like the function is continuous, one periodic, and also converge like the Fourier series converge absolutely of the unit box. So the problem of the L2 approximation is say, okay, we have this function, and the thing we want is a L2 approximation, which is a function of say n function evaluations. Of course, we can choose where we evaluate those functions, and once we get those evaluations, we want to get an approximation to minimize this kind of L2 approximation error given below here. And how this problem relates to the numerical integration? Well, because our function has a nice Fourier expansion, a very natural way to approximate this function is by another Fourier expansion. So here we have a Fourier series over sum over the subset I here, and then we have coefficients. Well, we of course don't know the true Fourier coefficient, but notice that the Fourier coefficient itself is the integral of some function. So you can use the usual numerical integration method to approximate this Fourier coefficient. Here I have the f tilde, and you replace the true Fourier coefficient by the f tilde, and then this series becomes the L2 approximation to your target function f. And you can imagine you can have a good L2 approximation if the index set I is good enough and the approximation here is good enough. And in particular, you can replace it with the lattice method, where you integrate the functions, integrate the Fourier coefficient at frequency edge by the lattice method, where you evaluate the function values as lattice points. And then you do this replacement, and you choose a set i's, and this gives you a approximation. And you can notice that it's already like very similar to what was coming before. So you can do a similar CPC construction to approximate to minimize some kind of like approximation of the worst case error. And then if you import like alpha and gamma, you can run these CPC algorithms to select the generating vector z and get a convergence rate here is n to the minus alpha over 2. Well, the issue here is that, well, aside from like you actually need alpha and gamma and also the CPC runtime, the issue here is that if you actually don't sample your points as the lattice points, there is actually some least square based methods that can actually get you to n to the minus alpha. So I kind of have like a very big efficiency loss in terms of number of function evaluations. So previously people are justifying this by saying, okay, but you are evaluating this function over the lattice points, which allows you to do a fast Fourier transform. So actually you gain something in terms of like reconstructing the function. While the least square approach, well, it's least square, you need to do n cube arithmetics in general. So you kind of lose in that aspect. Well, so here is a kind of like a result where if you replace it by the median approach, you can recover that n to the minus alpha rate by still sampling on the lattice points. So what you do is that, okay, previously we have the Fourier coefficient approximated by a lattice estimator. So here we just replace it by the median lattice estimator I just shown you before, and then we still select the same set I here. And with this approach, you can actually get with high probability an error that's n to the minus alpha for any fixed function here. One thing I want to emphasize here is that we change the error criteria. So previously we have the soup also function. So basically, if you think about in an adversary setting, your opponent is allowed to first know what's generating factor z you choose and give you a nasty function for you to approximate. Here we kind of weaken the notion here. So the function is fixed, and we just generate a random set of generating vectors here, and then we get a high probability error bound like this. Which I think for practical problems, it doesn't matter because if you generate for instance, if you generate your vector z and use it for multiple functions, then maybe you care about the worst case error. But if you use a new set of generating vectors for each new problem you encounter, then probably a more suitable error is this kind of like a fixed function error you can have here. Anyhow, let's start the proof. That's like the last proof in this talk. So first you can have the usual error analysis. So you have
Sorry,
the Fourier expansion.
want to
I
ask
know. You have the usual. It's about to end because I'm not going to talk about the part 4 anymore. So you have the usual Fourier expansion here, and then you have our approximation for f, which is given like this, and then you can have the L2 error measured like this. So for everything in I, you have the approximation error, and for everything outside I, you have the you basically measure it by 0, so you have the entire error. But if you choose I to be large enough, then this term is like small to compare to error threshold. So let's focus on the first sum here. So you can reproduce what we have before and get an error bound that's like n to the minus alpha, But so first we need to do the error bound for each edge in I. So before we actually do a sum over edge. So here first we reproduce the first step, which is the probabilistic bounds. So we have the error for one single edge, which is bounded by you can see like the first term here is if you still remember like the NZD letters, which I said is always in the dual nets. So in this context we actually need to single it out to do a more careful bounding. And so for the remainder term, we can actually bound it by something even tighter. It's n to the minus alpha minus 1/2. And the other parts are the usual thing. Yeah, actually solve. So the proof is very similar. So let me go a little bit quickly since we are going out out of time as well. So because previously we have the integrand here. And the arrow is looking like this. So here we are integrating the edge Fourier coefficient of f. So you replace f by the integrand f times this exponential term. So which gives you the error term now looks like this. You have the sum over L over the dual letters, and then the coefficient is like h plus L. So basically you have a shift in terms of edge. And then your error bound, of course, can be bound by these two sums, where you single out the NDZ net, as I said, and then you have the second sum here. And all we want to prove is that, okay, this thing is n to the minus alpha 1/2. And what you do is very similar to what you did before. First, you notice that for HL in the dual letters, the probabilities in the dual letters is bounded by 1 over n minus 1. And then you choose a set. So here our set K is depending on the frequency C edge. So with this, so for integrating this frequency edge, the relevant set turns out to be the smallest R edge plus L here. And then again, we have the same cardinality here with a union bound. We know that the K edge intersecting with the dual letters is empty with probability at least 15 over 16. And then we do the same step here. Okay, what's that? What's the definition used for the median? I didn't. Yeah. Thanks for this question. So yeah, for the median of a complex number, what we do is we take the median of the real part and the median of the complex part. So both of them are the median of like real numbers. Yeah, sorry, I forgot to mention that part. So anyhow, the remaining proof is very similar. You just do a conditional expectation, and the remaining step is basically the same. For anything in the K edge, due to this conditioning, it's not in the sum. For everything else, you include it in the sum, put it 1 over n minus 1 as before, and then you do a Cauchy-Schwarz. And the first sum as before, you can bound it by 1. And the second term here, it's basically the same algebra we have summed before, except this time we have a shift in terms of edge, which actually doesn't matter because we also shift our k by edge as well. So it's the same algebra, and if you recall the previous result, before taking the square root is n to the minus 2 plus 1. After taking the square root is n to the minus alpha plus 1/2 divided by n. That's how you get n to the minus alpha minus 1/2. And you do the Markov inequality as we did before. So anyhow, it's basically the same proof with a little bit more twists here. And then we do the same median trick here. You have this error bound bounded with successful probability of 7/8. By doing a median trick, you can actually, with failure probability expansion small in R, you have the same bound, but now for the median of this thing, which is, so this one is the median of the a real number, so it's well defined. And then you can put the median inside here, and here I put a factor of 2, precisely because the issue I mentioned. I take the median of the real part and the imaginary part separately, so just to be safe, I put a factor of 2 to bound this term. And now we can just sum everything together. So this thing is bounded by this, and then you can do the sum over I here. Here I did another. Okay, I guess I will run out of time. So anyhow, so basically by a union bound, you can actually have this bound uniformly applied for everything in I, and then you can do this sum, which both of them can be n to the minus 2 alpha here. Yeah, I guess I just need to practice for long talks. So anyhow, let me just state the theorem here. So for every function with this unit norm, then for Z1 to ZR, you just choose uniformly from the candidate set. The approximation error is with high probability n to the minus alpha with the usual dimensionality independence condition. And here's a comparison where you have the CBC construction with a stronger error criteria but a slower error convergence rate versus the median approach, which is for fixed function with high probability, but you have now n to the minus alpha convergence rate, which is much stronger. And I didn't talk about how to choose I guess, well, I'm running out of time anyway. So function evaluations and time to evaluate, that's not important. So anyhow, let's, I guess, just skip the last part. So let me just take, so the take-home message is basically, it just really helps to think in terms of high probability error bounds. It gets you better error convergence rates. It simplifies your design. You just choose generating vectors randomly. It requires less prior knowledge. You don't need to know alpha and gamma. It's very user friendly. It's much easier to do than CBC construction, and also you can write fancy paper out of it. So yeah, I think it's just helpful for us as researchers, and that's the end of my talk. And thank you for listening.
Thank you for this interesting talk. Okay, so Raoul, you had a question, but maybe